Hi, another video about my new NanoVNA. So at the moment I'm measuring the S11 coefficient of this low-pass filter as I did in my previous two videos. By the way, if you haven't seen them, check out especially episode 33 where I describe exactly what this S11 coefficient is, and I measured it both the NanoVNA and also using other instrument, the spectrum analyzer here and then the oscilloscope together with the signal generator. This was done to confirm the accuracy of the measurements done with the NanoVNA. Anyway, the point, let me zoom in a little bit. So this S11 coefficient really is a complex number. So this was explained also in the episode 33. So let me use this. I hope you can. I hope it improves a little bit the focus of this camera. Anyway, so all the NanoVNA is measuring at the moment is this complex number called S11. However, here in as you can see the NanoVNA interface, you have many ways to depict this information. So here we have a log max, log magnitude, log mag information. It says minus 18.5 dB. We have a phase information. It says 143 degrees. But we have also other information. The Smith chart says 41.3 ohm and 125 nanohenries, if you can see. So let me see if I can. Yeah, okay. Other type of visualization are the SWR. It is saying 1.26 at the moment. And other things, for example, I have polar. It says here minus, I don't know if, let me see if I can focus. Anyway, it says minus 0.09. And 0.07 J. So all these information are in fact equivalent one to each other. And in this video I would like to tell you how to do the calculations to move from one to the other. So these calculations are done, of course, completely automatically by the NanoVNA instantly, and for all frequency in the range being swept. But I think it could be kind of interesting, at least it is for me, to understand what's going on behind this calculation, and it's also useful to understand the meaning of all these numbers. So in this video I'm going to show you how these calculations are made. Okay, so I took all the information provided by the NanoVNA, all the data that it provides, and copied them here. So the log, mag, phase, Smith chart, SWR, and the polar display. And all this data has been collected for a very specific frequency, which is 7 megahertz, 542 kilohertz, and 500 hertz. Of course, the NanoVNA collects all this data for all the, rather for 100 points in this graph. So here we are, of course, just considering one point, and all the calculations, can be made for all the points once you have these informations. So I'm now going to basically describe how to process this information. Before I start, I could use any scientific calculator like this, for example. Okay, this is just one you can find in the browser. However, I prefer not to for a couple of reasons. First, okay, this would have all the trigonometric functions we need to do the calculations. But like all other calculators suffer from rounding errors. For example, if I take 1 and I divide it by 3, you've probably seen this so many times in your life, it gives you this 0.33333. And then if I multiply it by 3, I get 0.9999, right? So I started with 1, and by dividing by 3 and multiplying by 3, I got something smaller. Okay, this is not very significant in every physical terms, I agree, but it's still an annoying error. Instead, there is a tool you can find for free online, which is called the Wolfram Alpha, and this is a much more sophisticated calculator. It's a symbolic calculator, so if you write an expression 1 divided by 3 multiplied by 3, it does not calculate an approximate number like this 0.9999, but it calculates the exact result, as you can see here, 1. Furthermore, it has support for complex numbers, whatever. This is a very advanced tool. It comes from this Wolfram company that produce a very advanced tool for mathematicians called Mathematica for symbolic calculation. And so this is basically the browser version of it, and it's really, really advanced. So I'm going to use this. Okay, so before I start, let me tell you what's going on here. All this data that we have are presentation of just one measurement, as I explained in my video, episode number 33. And this measurement is called the S11 value. Okay, this S11 value, from this value, from this S11, you can recover all this information. But what is really measured is this S11. This S11 is a complex number. Okay, so complex numbers can be identified with points on the Euclidean plane here. So they are just vectors. Okay, they are points in this vector, in this plane. Perhaps the simplest way, the most direct information that we have in this list here is polar. Okay, it says that the point we are looking at, S11, is located at minus 0.09 on the x-axis. So if I, for example, place here minus 0.1, well, perhaps this is our minus 0.09, okay? And if here I place a plus 0.1 on the imaginary dimension, this vertical axis, well, perhaps our 0.07 is going to be, I don't know, something like here perhaps. So our S11 is going to be here, okay? So this is what the NanoVNA is measuring now, this point here. So the polar display actually shows us, give us this data. If we go actually to see this polar display, let me show you polar. So the data minus 0.09 and plus 0.07 is displayed on the top here. But here we see exactly, you know, we see the plane basically, and so the point is exactly here, okay, on the top left quadrant here. Okay, another way to see what, another way to describe where the complex number S11 is to look at it as this arrow, this vector. And so to specify the length of this arrow, and also the angle that this arrow has with the x-axis. Okay. Once you have these two data, you can basically find uniquely this point. Now this angle is this face here. So as you can see, is 140 degrees, which is more or less correct. Okay. So this is of course 90 degrees. This is 180 degrees, and so this is something in the middle is 143. Of course, I depicted things very roughly here, but so here we have our 143 degrees, which is this value here. The other values are a bit more mysterious. So this log mag, the Smith chart, and the SWR. So let's see how we can compute them using Mathematica. So the first thing here is, so let's focus first on log mag. Here I have already set up the calculations. So this, we already say that this angle here, let me call it theta, is the phase. So theta here is 143.61 degrees. But what is the length of this vector? Let me call it m. So the way to compute from m, so this length, we don't know at the moment, the way to compute log mag from that m is the following. Log mag is going to be 20 multiplied by the logarithm base 10 of m. Okay? So in Wolfram Alpha, I can just write this equation, and from this equation it will find the m. Okay. So let me press enter and see the calculation running. So it's doing a lot of calculation symbolically. You see, it's doing a lot of things. And at the end we find that this m is 0.11. Well, let me just write 0. So m here is 0.119, okay, more or less. So from this m we can obtain the log max, and vice versa. From the log max we can obtain the m. And in fact, given the m and the theta, we can rediscover also the polar form, okay? And so this is done here by these calculations that, you know, if they are useful, I wrote here in case they are useful, but basically what I'm saying is this. So I'm calling A for the angle. So what here I call the theta is called A at this point. And I'm converting from angle to radians, okay? So this is what mathematicians use most of the time. They are not using degrees from 1 to 360. They are using radians that goes from 0. Here we have pi. Here we have 1/2 pi. And here we have 3/2 pi, okay? So this is going to be 2 pi equals 0. So I'm converting from degrees to so from degrees, which are 143, to radians, and I'm calling this value A. And then I'm saying, look, let's call R the complex number which has a length, so the complex number, the vector, that has a length of m. And I just, you can write like this in Wolfram alpha very simply, and as a angle, so the theta here or the A, it has A. So when we do the calculations, we rediscover basically here, this R, the information that we already had at the beginning, right? These informations. So the point of this calculation was to show that given the log max and the phase, we can rediscover the polar form. And of course, vice versa, given this polar form, we have log mag and phase. Okay. Moving on, we have, let me check what we have calculated here. We have the polar, we started from there, and we also computed phase and log mag. In reality, these two together allow us to recover polar and vice versa. Okay. So let me, yeah. Okay, so we still have to look at the SWR and Smith. So regarding the SWR is very simple. The SWR, once you know this m, you can compute the SWR. So in particular, the SWR only depends on m. It doesn't look at the theta. Okay, so it's only partial information. From only the SWR, we cannot recover the whole complex information S11. And the way to compute this is there is an equation here. You can find many places. Gamma here is the letter used where I used m, okay? And so if you set up that calculation, so m we already calculated, and so I'm calling s this SWR. I run the calculation, let's see. And I'm obtaining the value. Okay, so as you can see here, Wolfram alpha is calculating an exact value, so as a fraction. It's not giving me an approximate number, but I can ask for an approximate form, and it's telling me that it's 1.27001, and here we get basically this number. So the NanoVNA is only showing the first digit, but in reality it's 1.27. We just calculated that from the other data. Right, and then we have to move to the Smith chart. Okay, so I started a new page to have more space. So far we have understood that the NanoVNA is calculated as S11, which is this complex value, this vector. So it has some Cartesian coordinates or a length and an angle with x axis here. And now let's look at the Smith chart. The Smith chart is giving us a value, 41.3 ohm and 123 nanohenry. So this is a complex impedance. Let me call it Z or Z. And it is the complex impedance of this device here, the device under test. Okay? The relationship, there is a direct relationship between this complex impedance Z and the value S11, and it is expressed by this equation. So it's the equation that says that S11, let me write it, I cannot do two things at the same time. Okay, yeah, so the equation says S11 is equal Z minus 50 ohm, and this is because the NanoVNA has an output impedance of 50 ohm, divided by the Z plus 50 ohm, okay? So from S11, which you already know precisely, we can compute this Z, but also vice versa. Given Z is simple to compute S11, okay? So from the data from the Smith chart, we can go back to S11. So anyway, this complex impedance is itself a complex number, so it's going to be some point in the plane, I don't know, for example, here. And so it's going to have some coordinates, Cartesian coordinates, a length, and as usual, some angle, let me call A. Right, so let me call O for this the length, okay? So it's compatible with what I already written here. Oh, I misclicked here. It's compatible with what I've written here. So here S stands for our S11 with the data that we already computed, okay? So on the coordinate are 0.0957843 on the x-axis, and on the y-axis is 0.07, etc. Okay, so I'm setting up here the equation. Okay, so it's a variant of the equation. So let me actually write it as I just did on paper. So it's completely equivalent. Okay. You see, so now is exactly the equation I wrote on paper here. And here I'm calling O the magnitude of this complex impedance. So the magnitude of Z is going to be O, and A is going to be the angle, just like with the nomenclature I used on paper. So let me run the code here. Okay, and so we get our results. And so as you can see, we have that O is 41, so O is 41.2988, and as you can see, this is our value in ohm. Okay, so in the Smith chart, when you see this value, it is the length or the magnitude of the complex impedance of the device under test. And we also get here the angle, which is 0.14225. Okay, but what about this value, the 123 nanohenry? How is it calculated? So this value is calculated on the basis not of the angle, but on the basis of the vertical coordinate of this vector. Okay, so let me show you the next page here. So the next, by the way, from this previous computation, we know that this imaginary coordinate is 5.85. Okay, so it's the value here. Something. And so now we are setting up this equation to express this in nanohenries. We have that an imaginary impedance, so let me write it this way, an imaginary impedance of 5.85 comes from an inductor, and so it must be of the form, this is a standard equation, 2 pi L, this is the inductance in a Henry, multiplied by the frequency, okay? So we are setting up this equation, and that's what is being done here. So as you can see, I exactly wrote I wrote, where f is the f we started with, so it's 7 megahertz, 542 kilohertz, and 500 hertz. So let me run this. And here we are getting an exact result, so let's approximate it to see precisely. And this is our, so we are getting a value for R of 123 nanohenry, more or less, as you can see here. And this is what we had at the beginning given us by the NanoVNA. Okay, so I hope this discussion was somewhat useful. So you don't need to do this calculation, of course, neither with Wolfram Alpha or absolutely not manually. The NanoVNA is doing all these calculations for you, but it's perhaps useful to know what this number means and how you can compute one from the other. Okay, so we have finished all the calculations. Before terminating this video, I would like to make a comment or a remark. So in this video I took the position that the S11, which is what is being measured here by this VNA, is a complex number, okay? So it's a vector in the complex plane. It has a magnitude m and a certain angle theta. This is mathematically perfectly fine, so it's just a complex number, and based on this fact we can do calculations based on the arithmetic on complex numbers. And it's a vector, and this is why these things are called vector network analyzers. Perfect. But we should not forget what the S11, it is a complex number mathematically, but what does it mean, this complex number physically? So I'm going just to remind you about this. So here we have our VNA, like the Nano, and it has an output port, this port here, and from this output port is emitting a signal, okay? So this signal is going to have some amplitude, A, and it's going to be a sinusoidal function, sine, and some frequency, okay, or period, W. So it's something of this form. This signal is entering the device under test, which is in this case was this low pass filter. So it's entering here, and depending on the input impedance of this device under test, so the Z here, there will be some reflections, okay? There can be 0 reflections or 100% reflection, but in general the reflection looks like the original signal. So it's something like this, but the amplitude is attenuated, so there is basically a coefficient we are applying to this amplitude. Let me call it C, and what is being returned has the same frequency but potentially can have a phase difference, okay? So in general this C is an attenuation factor, so it's going to be a number between 0 and 1, okay? If C is 1, we are getting back the signal with its full amplitude. If it is 0, we are getting back, basically this becomes 0, and we are getting absolutely no reflections, okay? So what is being measured, the S11, what it physically means, the M here of the S11 is just C, and the theta is the theta that we have here, okay? So it's basically a way of describing by these two values the way that reflection occurs in the device under test. One last comment, we saw in the video this equation that S11 is related to this Z by this equation, so it's Z minus 50 divided Z plus 50, okay? So this means that when this is a perfect, which exists only in theory, but it's a perfect 50 ohm load, here we get that the S11 is going to be 50 minus 50, which is 0, divided by 50 plus 50, 100, and these all things become 0. And so that's what we expect when this is a perfect 50 ohm load, this C becomes 0, and the reflection is absent, is completely 0. Okay, so with this I'm going to conclude this video, and I hope it was helpful and shed some light on this mysterious numbers. And if you have any comments, feel free to leave them in the section below. Thank you very much. Bye bye.